If physics has taught us one thing, it's that nature's a mathematician. But she's picky and uses only some maths. Why this maths and not any other? A group of researchers has found some intriguing regularities in the mathematics of physical laws that might bring us a step closer to finding out. Before we talk about maths, a big thank you to our supporters on Patreon, especially those of you in Tier 4 and higher. On our Patreon, you'll get the full transcripts with links to all sources, so have a look. Every little bit helps. We often speak of mathematics as a language, but it's not like any other language. In any language besides mathematics, words refer to something else, to reality, or at least our ideas of reality, which I'd argue are also reality. But mathematics is entirely self-referential. It doesn't refer to anything besides itself. That's for what pure mathematics is concerned, but when we look at the mathematics in physics, it again becomes a language of something. It becomes the language we use to describe our observations. So why this particular maths? Spoken languages are known to follow certain regularities. The most famous one is Zipf's law. It says that there is a regular decrease in the frequency of words. If you assign each word a number, the most frequent word is number 1, the second most frequent word number 2, and so on, then you find a regular decay of the frequency with their assigned number, or more technically a power law. This is Zipf's law. This law has been found in text bodies in pretty much all known languages, and while there are some differences between languages, they clearly all have a lot of regularity. Just why that is so, scientists haven't yet figured out. Linguists speculate that it may be the most efficient way of communicating information, which you'll immediately understand if I repeat that it may be the most efficient way of communicating information if I repeat the relevant information. Somewhat off topic, but there are speculations that this is the reason why the knowledge increase in large language models slows down following similar power laws. That language has these regularities also raises the question of whether we have something like that in the language of mathematics that we use for the laws of nature. The authors of the new paper studied this question by taking apart the syntax of equations into mathematical operations. For example, addition and multiplication, or taking the second or third power. They also included multiplication with a constant of nature and more complex functions like an exponential function or trigonometric functions. They then counted the frequencies by which these appear in 3 different samples: the Feynman Lectures of Physics, a Wikipedia list with equations, and a paper called the Encyclopedia Inflationaris that lists a lot of models for inflation, so a lot of equations. What they find is that the frequency of mathematical expressions does follow a law, but it's not the same as in languages. It's not a power law decay, it's an exponential decay, and it's surprisingly regular despite the actually quite small samples. This is very intriguing. Where do these regularities come from? There are 2 possibilities. One is that this tells us something about the mathematics which appears in the laws of nature. The other is that it tells us something about the way that we use this mathematics. These possibilities are not mutually exclusive, and I suspect that the right answer is a mix of both. The human contribution is that we tend to rewrite equations in ways that we find easy to decipher just by looking at them. A computer might not care, for example, if you factorize terms. We do it because it makes it easier to see what's going on. It's a similar thing when it comes to why the powers of quantities in our laws are mostly integers. There's nothing preventing us from defining a unit for the pith root of energy, except sanity, or the risk that it'll make every physics class spontaneously combust. So there is clearly a human element in this, which is simplification to a notation that we're used to dealing with. But that leaves the question of why the laws are so that these simplifications work. I think there are some deeper truths to be found there. For example, that we very rarely have fractional powers of quantities probably tells us something about the origin of dimension 4 units. It's also a curious fact that in physics we usually don't have more than two time derivatives. There is no deeper reason for why that should be the case, except that it doesn't describe what we see. Physicists are so used to this, I think, that they, for the most part, don't even think about it anymore. But it's a curious example of this math and not another that makes me think we're missing some underlying structure. Or maybe the universe is just trolling us. Why do we still not have flying cars? It's so frustrating. It's like with these robot demos. Looks great, where can I buy one? Unfortunately, reality is far behind the flashing demos. The future, so we've been made to believe, is that of eVTOLs, which are electric vertical takeoff and landing aircraft. They've also become known under the name air taxis, but for me, they'll remain flying cars. They're drones, basically, but big enough to carry people. Flying cars could be a blessing for cities that are suffocating in traffic but have no space to build more roads. They could replace short-haul flights and save kerosene. They could become airborne ambulances or carry time-sensitive cargo. They could open entirely new opportunities to prematurely die. And that brings us to the problems. Air taxi startups have been around for about 15 years, and many of them have gone out of business already. It's not that these things don't fly. We've seen many demonstrations of prototypes. It's just that making them commercially competitive takes a lot of investment, much more than anyone anticipated, and startups are just running out of money before getting anywhere. The most recent victim of a funding shortage is the German company Lilium. It was founded in 2015. In 2022, they presented a nice prototype that took off and landed flawlessly. They had about 1,000 employees, 700 plus pre-orders, and more than $1.5 billion in investments. It wasn't enough. Last week, the company announced its insolvency. Stocks of the publicly traded company sharply dropped afterwards. The UK company Vertical Aerospace, which works on a similar product, ran into the same problem earlier this year. They were narrowly saved by a $50 million private investment of their CEO. Another German company, Volocopter, raised more than 500 million euros, but a few months ago its CEO raised insolvency concerns after the German government didn't want to give them a 100 million euro loan. They aren't the first to run into trouble. Kitty Hawk, founded in 2010 and backed, among others, by Google co-founder Larry Page with a total of more than $400 million, closed down in 2022. Zunomero, one of the first companies to enter the business, laid off people in 2019 and not much have been heard of them since. Why is that happening? The trouble is that the world has been built around fossil fuels. Any company aspiring to commercialize electrically powered flying machines needs to have enough breadth to build the entire production line, from batteries to docking stations, along with it. Currently existing batteries are too heavy to allow for long-distance flights, which limits applications. On top of that come regulation worries. You don't want taxis to fall down on people, and no one really knows how the regulations will look like. This somewhat understandably spooks investors, though maybe all we need is a new complaints department. But as they say, there are only 3 things you can count on in life: death, taxes, and startups running out of money, so it's not like this is unexpected. One also expects, I'm afraid to say, that they falter first in Europe. This is because the US and Chinese governments have been putting much more money behind the idea. Their startups are better funded and will last longer. Whether that's a good thing and will eventually lead to success, or whether it just means that the US and China will sink more money into a business that isn't ready to fly, is another question. Seeing that the biggest problem with air taxis is that they're electric might make you wonder, why not just use combustion engines? Leaving aside that they're inefficient and we're supposed to stop using them, The issue is that they're too noisy. You don't really want lawn mowers to hover over your house, do you? One way to fix the battery issue would be to use hydrogen. This is, for example, what the Boston-based firm Alaka'i is working on. The name is Hawaiian and means to lead or to guide. They have a prototype that they say can fly up to 4 hours at more than 100 miles per hour and carry more than 1,000 pounds. This all sounds very good, but in the end, the question of whether that makes commercial sense will come down to the question of where the hydrogen comes from. Again, investors might be wary. When it comes to steady financial support, I suspect that Chinese companies will have an edge. The Chinese government has flying cars in their 5-year plan, and they're prepared to pour a stunning $44 billion into what they call the low-altitude economy by 2026. It might mean that China will lead the way into the future, or that China will lead itself into the past. We shall see. For the moment, I'm jealous of the Chinese because I think this is a very sad development. I understand the economic problem. I understand that investors and governments don't want to throw good money after bad, and I'm glad I didn't buy Lilium stocks. But I also think that flying vehicles are the future, and I want the future to be here, now. Or maybe we should just accept that the Jetsons were a particularly cruel joke. The ether was a 19th century idea that has soundly been rejected by evidence. Then how is it that there are still physicists working on ether theory? And indeed, a new paper seems to come out on this every couple of weeks. Little Albert is understandably very confused. But I have answers. Ether is a Greek word that roughly means fresh air. It was supposedly what the gods were breathing up in the heavens as they were debating where the next lightning bolt should land. The word was later used among scientists to refer to a medium that filled all of space and that allowed forces to travel from one place to another. Newton, for example, entertained the idea that the gravitational force was transmitted in the ether. But the idea became most closely connected with the question of just how light, or electromagnetic radiation in general, travels through empty space. This problem arose in the early 19th century after optical experiments, for example prisms and interference, clearly demonstrated that light behaved as a wave. But at the time, scientists knew only 3 types of waves. Waves in water, waves in air, and waves goodbye to their social life when they became physicists. So if light was a wave, what was the thing waving? Well, that was the ether, or more specifically, the luminiferous ether. The ether itself defined what it meant for something to not move or to be at rest, as physicists say. This idea had it that Earth was not at rest, but sloshing through the ether on its path around the sun and dragging parts of it along. However, they already knew that if there was any such ether drag, it would have to be small because of an effect called aberration. The positions of stars change along our path around the sun, and an ether would seem to move them differently than we observe. And knowing that the drag had to be small, light going into different directions on Earth would have to move at different velocities depending on whether it was going along with the ether or perpendicular to it. The Michelson-Morley experiment famously proved this to be wrong. Light moves at the same speed in all directions. There is no ether that defines what it means to not move. Einstein was right. All motion is just motion relative to something else. Scientists resolved to accept that light is a wave, period. It travels in empty space and doesn't need a medium to travel in. But the idea of the ether made a comeback. We know today that the universe is filled with electromagnetic radiation in the microwave range that was left over from the Big Bang. This cosmic microwave background is often depicted like this, but actually these are only the temperature fluctuations of the CMB, which are ridiculously tiny. The CMB has almost exactly the same temperature in all directions, about 2.7 Kelvin, if you don't move relative to it. Earth does move relative to the cosmic microwave background, which is why its temperature is hotter in the direction that we're moving and colder into the other. This is called the CMB dipole. In other words, the cosmic microwave background tells us what it means to be at absolute rest with the universe. Technically, the cosmic microwave background indeed affects the speed at which light travels, because there is a minuscule chance that a photon from a star actually interacts with a photon in the cosmic microwave background. But this effect is so ridiculously tiny as to be unobservable. By the way, this video comes with a quiz that lets you check how much you understood. The fact that the cosmic microwave background is a sort of ether that's compatible with Einstein's theories brings up the question of whether the universe might be filled with some Einstein-compatible ether. This is called the Einstein ether theory, and it was introduced by Ted Jacobson and David Mattingly 20 years ago. The Einstein ether, like the original ether, defines what it means to not move. It's usually, but not always, assumed to be relative to the cosmic microwave background. The difference to the original ether is that it doesn't affect light because that's been ruled out. When I say it doesn't interact with light, I mean it doesn't interact with light in any other way than gravitationally. Because like any sort of extra stuff in the universe, the Einstein ether has gravitational effects. Indeed, it can mimic dark energy quite easily, and some have argued that it could even account for dark matter, though the latter turned out to be difficult to make work well. And this is why you're seeing papers being published on this every couple of weeks. This comes from physicists who are trying to understand how well the Einstein ether works with observations from gravitational lenses or with supergalactic structures and so on. So if this new ether can explain dark energy and dark matter, then why don't we just use that instead? It's because mathematically it's not an advantage over using dark energy and dark matter. The Einstein ether is a rather flexible model. There are many types of ether, and if you have sufficiently many parameters, you can make them fit to any data. Basically, we're missing a good reason to believe in it. Like with dark matter, physicists have tried to look for the Einstein ether directly. If this ether interacted with particles in the standard model, then it would have observable consequences. It could allow processes that are otherwise impossible, such as an electron that spontaneously emits photons, or particles that are being slowed down at different rates depending on their spin, an effect called birefringence. And you guessed it, none of that has been seen. This doesn't rule out the idea, it just means that if the Einstein ether exists, it's exactly as annoying as dark matter in that it doesn't want to reveal its secrets. In summary, yes, ether theories still exist, and yes, they're compatible with data, but it's not the same ether as the one that was ruled out a century ago. The new Einstein-compatible ether might be an alternative to dark energy and/or dark matter, but at the moment it doesn't have any distinct advantage. I have a theory according to which physics itself moves through an ether of ideas, dragging some of them along through the void of academic journals, proving that ultimately humor is always relative to the observer. Have you been holding back opinions recently? You're not alone. Self-censorship is on the rise, also in science, and it's a problem. When my daughter was about 4 years old, she announced to my brother, "You have a very big nose." Children don't self-censor, but as we get older, we learn to not blurt out everything that pops into our mind. That's partly because of social norms and partly because HR keeps sending strongly worded emails about microaggressions, but more importantly because it's just not useful. If you want to negotiate a sale or welcome a new neighbor, telling them that they have a big nose isn't going to do much for you. And so we self-censor all the time, and often for good reason. reasons. But in the past decade, self-censorship has grown to worrying proportions, and not for good reasons. A survey among a nationally representative sample in the UK from earlier this year found that a whopping 76% of respondents say they have restricted expressing their personal views in public out of fear of receiving freedom-restricting harassment, which they define as threatening, intimidatory, or abusive harassment online and or offline, which is intended to make people or institutions censor or self-censor out of fear. Another survey from the UK Free Speech Union found that 62% of employees who had undergone diversity training at work say that they're afraid to say what they really think about this. The remaining 38% were busy completing their mandatory How to Have Opinions Safely training modules. It's not just a UK phenomenon. A summary of surveys in the US found that the fraction of people who feel that they can't freely speak their mind has almost tripled in the past 50 years. A survey among Facebook users in the US from a few months ago found that more than half avoid posting political content at all, and another quarter partially self-censors their opinions. The rest is your Uncle Bob, who still thinks that all caps is a valid argument. This also affects scientists, of course. A rather worrying example of this was recently reported in the New York Times. A study that has been running in the USA on the mental health benefits of puberty blockers in transgender children found no significant improvements. But the team didn't publish the result. According to the study leader, a vocal advocate of these treatments, they didn't publish it because their team don't want the work to be weaponized. They plan on publishing it eventually, but until then, more children in the US risk being put on drugs that might in the long run impede their growth, bone structure or fertility for nothing in return. Scientists are afraid to publish work because they think it might be controversial. And it's not an isolated incident. The American Foundation for Individual Rights and Expression has reported a stunning increase in the attempts to silence scholars for their work, both from the left and the right, most often for race-related topics. Many of these attempts use petitions like this one from some people who got offended about a paper that argued that colonialism also has benefits. And maybe some of you remember Alessandro Strumia, who dared analyze how much women in physics publish and get cited and found that they don't perform as well as men. He too became the target of a petition. A 2022 survey found that more than half of faculty in the US is worried about losing their jobs or reputation because someone misunderstands something they have said or done, takes it out of context, or posts something from their past online. And a whopping quarter of them said they were very or extremely likely to self-censor in academic publications. It seems that if you want to work in academia in 2024, the required skills are publishing papers, securing grants, and not touching topics that anyone anywhere could possibly be offended by. This is a bad trend, and I'm telling you about this for several reasons. First, I want you to know that I fully support any scientist's right to talk about politically sensitive topics. I think you should not let yourself be intimidated by some crazy people on social media. I've been dealing with these nutcases for more than a decade. We will outlast them because in the end, truth wins. Second, this seems to be mostly a US-UK phenomenon, but the same thing is happening in the EU. Indeed, there's been a peculiar episode in which the German Skeptic Society, out of all places, began to self-censor because they were afraid of Twitter mobs. Third, it's a fact that facts are sometimes offensive. Women are on the average shorter than men and slower runners. I find that very offensive. But what use is being offended? I think that a more useful reaction is to say, why the fuck are all treadmills built for men?